directly, change fonts. I mean, there is no such options, to change font size or font colors and these kind of things, because it doesn't have any meaning to the end users, particularly in terms of fonts. We have also discussed that, given these braille cells, they must have a very specific distance between the individual dots. Otherwise, it becomes very difficult for a person to, read and write, or to understand the individual cells. Similarly, there should be a fixed width between, two different words. And as a result of which, and similarly, there should be a good difference between the lines, right? And therefore, it becomes a very strict formatting issues when we discuss something about Braille. And therefore, it has been observed that a typical Braille page contains, a standard 40 cells in length with 25 lines of Braille per page, right? So this is the convention that every Braille printer, every Braille embossing has to follow. I mean, we cannot have 25 lines, more than 25 lines per page, and we cannot have more than 40 cells in a single line. So now, so this is a convention. This is widely followed in almost all the blind communities across the world. Now, one of the major issue with this is that as a result of such a low number of characters per page, the number of pages becomes very, very large. So in fact, a book, if you want to convert a entire book written in English to Braille, a book of 100 page maybe may take 500 or 600 pages when you are printing it in terms of Braille. And the book becomes very large also, because this page size is also fixed, right? So there is a fixed dimension of 11 by 11.5 inch size. So it's almost 1 feet of length across length and breadth, and essentially the entire page becomes very, entire book. If you are talking about printing a book, the entire book becomes very large and bulky. The issue is that how can we reduce some of these difficulties with respect to such a bulkiness, or in terms of, can we do any kind of contractions or any kind of technique that can reduce this number of problems. So one solution, and secondly, another problem with this Braille transliteration system is that, as I was discussing in the last class, that each of these Braille cells consists of 6 dots, right? So these are the 6 different dots that we use. But over the time, it becomes really very difficult for representing all the different kind of symbols and structures within these 6 cells. So, for example, there are different kind of formatting issues. There are issues related to hyperlinks, and there are many other challenges for which we have seen that these utilizing these 6 dots creates a lot of problems. Now, one of the solution for these problems is rather than keeping the 6 dot convention, 6 dot system Braille convention, we can have 8 dots. Now, the advantage of using these 8 dots is that you can accommodate more characters as well as you can utilize these last row for different kind of formatting issues also, right? So say for example, you are writing some text and you want to give a hyperlink, right? How can you do that? So typically in those cases, I mean, these the last row of 4 and cell number 4 and 8 are used to specify those kind of information. But again, these are essentially you will find that there are in the literature there are two different kind of dots drill dot systems. The more conventional one is the 6-dot system, which is widely used and everyone knows about this 6-dot system. But more the 8-dot systems are very recent incorporation, and not too many people are aware of these 8-dot systems, and they don't use this 8-dot system primarily because of the fact that the in order to make this 8-dot system, I mean 8-dot rail cells, the entire infrastructure needs to be changed. Starting from your printer, starting from your software that can write these 8-dot rail systems, everything has to change, right? And the learning process is also needed to be changed, because I mean people are more conversant with these 6-dot systems in their educational academics. Everywhere they are more conversant with this existing 6-dot system. So somehow, I mean, this 8-dot convention didn't materialized in the community. But still, I mean, to a large extent, I mean, in many places you will find these 8-dot rail systems, which is widely used in many countries. But particularly, I mean, when we will discuss about multilingual systems where braille can be represented in multiple languages. So uh, there we will find, I mean, in many of the countries like China and Korea, they use widely these 8-dot convention systems, because it helps them to represent more and more alphabets or characters using these convention systems. So and another advantage of using this 8-dot system is that you can reduce the number of you can increase the number of uh, uh, alphabets within a single page. So more and more content can be placed within a page rather than utilizing the 6-dot system. As I was discussing in the last class, that there are some situations where for a single English alphabet or English ASCII character, I mean there can be multiple braille cells, right? So here I think we were discussing about, yeah, I mean some of these characters, there are multiple braille cells. If specifically if we follow the 6-dot braille systems, but if we have a 8-dot braille system, then I mean these two cells can be merged together and they can have a different representation in an 8-dot system. So we don't need two cells to represent one character. Using the 8-dot system, we can have only one cell for a single character, and which drastically reduces the space, and we can pour more content in one single page. And why we are discussing is that because not only in terms of bulkiness, but these pages are costly, and therefore when you are thinking about printing something in a bulk, say for example a book or multiple books, then you have to think about all these aspects. I mean, if you can reduce a few pages within a book, then it reduces the cost of the book drastically also. So another important way of handling this challenge is maintaining the existing 6-dot systems but then can we reduce or can we compress some or can we can we compress these words in some way. So what actually we mean by compressing? So we typically in English also we do a lot of compression when we write or when we talk about something. So say for example, I mean in English we typically use this term as don't, right? Instead of the full word, I mean full word as do not. So do not is represented as don't, then cannot uh, is typically written as can't, right? So essentially we do some kind of compression, and then and it becomes very conversant for people to understand. So essentially, so these kind of compressions becomes very important when we are talking about braille representation, because they reduces uh, the page size and increase the number of contents that can be put in one single page. So and typically this compression is called as grade 2 braille transliteration or the grade 2 braille, and the standard one, the conventional one, is called as grade 1 braille. So what are the different kind of these compression or contractions can be possible? So one of the thing is that if words are too frequent, I mean there are so some of the English words, so whatever we are discussing in terms of English right now, and we can assume that if there are many words in English which are very frequent, right? So say for example the standard determiners or articles, so these words are a preposition, conjunctions, these are very frequent words, and for each of these words, say for example the word like therefore, uh, right? So the English word therefore, actually you will see it's a long word. uh, so it will take 1 2 3 4 5 6 7 8 9 cells, right? But this is a word which is quite frequent, or the word the uh, then the word where. These are very frequent English words, very frequently used by us and commonly understandable, commonly used, right? So, can there be, I mean, a mechanism through which instead of representing the entire word therefore by 9 different braille cells, can we have say, I mean, 2 cells which is going to represent this entire collection of characters. Similarly, for the word the, which is the most frequent word in English, I mean, top 5 or 10 frequent words in English, can we have a separate single cell representation of braille, right? So if we can have these kind of contraction, then it becomes very uh, convenient to reduce the size of the braille page on the in terms of the entire size of the entire book. So I mean, but these contractions cannot be done randomly. So we cannot contract all the words. I mean, we can contract all the words, but how can we, decode in that particular case? So once the main challenge with this contraction is that in terms of decoding. So maybe we can represent this therefore with two braille cells, but when a person is reading, in that case the person has to be aware that these 2 cells should correspond to a particular this word therefore. So they should have that kind of knowledge intact with them. And typically we will see, I mean, there exists certain kind of dictionaries where I mean these the collection of frequent words are already there, and their corresponding contracted braille representations are also there. And during a person's study, they used to learn these kind of contraction mapping, the grade 2 braille transliteration mapping. So there is no such technique available as such, to automatically decode these kind of contractions. But over the time, when they are conversant with the reading of braille, they remember, what are the contracted form, and there are special symbols that that tells us that okay, this particular portion of the text is is a contracted form of the braille. So there are certain conventions that are also followed when we do some kind of contractions, and one of the technique is contracting in terms of the suffixes or prefixes. So in English, we have it is a term that we typically study in natural language processing called morphology, right? So what morphology is, it's a study of how we can create new words, or we can change the meaning of the existing words by attaching suffixes and prefixes. So when I am writing the word play, right, and if I am attaching a suffix like ing, so play is a verb. When I am attaching a suffix like ing, it is forming a new kind of word called playing, which is again a verb in its continuous form, right? So similarly, eat is contracted attached with a suffix ing, which is forming eating in a continuous form. So what we can see is that these kind of, typically what we will I think most of you have already studied these things in your English high school English grammar, that we typically attach different kind of, there is a concept of root word. So there is a concept of root word, and then we attach some kind of suffixes to form a new word. Okay, so a new word. So typically these suffixes are very frequent. These suffixes are very less number. There are countable number of suffixes are there, and most of these suffixes are already known to us, which are and therefore one way of contracting is instead of putting all these words, we can contract these suffixes into a single cell, right? So instead of contracting the entire word playing, which will put a higher burden on the reader, to memorize all the possible kind of contractions for all different words. What we can do is we can identify these kind of frequent character sequences in terms of suffixes or prefixes, and then we can do this kind of contraction. So in Braille, what will happen is, given the word playing, we are going to right here we are representing. So as originally we have seen, we are getting the word playing. So for the first root words, we are having the similar representation as we have done for the Braille transliteration that we have already seen. So for individual words, individual alphabets, there will be a Braille transliteration. But for ing, since it is a very frequent suffix, we are having a contracted form like this. So one cell is representing character combination of 3 different character combinations, right? So similarly, sing will also become, so since ing is, so here here actually the person, or we don't care that whether this ing is a suffix or not. So we are mainly concerning with these character sequences, right? So ing is a very frequent character sequence, and therefore we are representing it with this particular cell. So similarly, I mean, sing, here you will see that ing is not a suffix, right? So it's a part of this, the entire word, sing. So sing doesn't comes from s plus suffix ing. So, but still, since ing is there, and we already know that ing is a very frequent suffix, and this there is a contracted representation of this ing, so it is going to be represented like this. Right. Similarly, there can be other suffixes which are very frequent, like ed, right? So play plus ed becomes played, right? So similarly, what we are doing is this ed is a suffix, and we have a contracted form of ed as this representation, and therefore we have a contracted form of played. Uh, on the other hand, in the word like edge, you will see since ed is, again, I mean, here ed is not a prefix or a suffix, but it's a part of the entire word, but still it is going to be represented in terms of these kind of contracted form. So this kind of contraction are typically called as part word or partial contractions of Braille, where a part of the entire word, where there is a portion of the word which are very frequently used character sequences, those are getting contracted, and not the entire word. And then there are the full word contraction, or the whole word contraction, where for all the, I mean, the entire word has got a contracted representation, and typically these are the words which are typically these are the determiners, prepositions, conjunctions, and so on, which are very frequent in English grammar. And the issue is that how we are going to recognize them. We have to have a dictionary where all these words are frequent words are written. Essentially, we are talking about words, but these are, for blind people, these are not words but a sequence of characters, and these characters are actually represented by these the contracted Braille representations. And they typically stored in a dictionary from where they can refer also. I mean, what are the contracted form of a given word. Now there are some more contraction rules probably. Yeah, like, I mean, so some of the contractions we also as a sighted user we also often do, which is in terms of texting language. I think, I mean almost all of you are aware of this term as texting language. The language that we typically used in social media or maybe in SMS, where again, I mean, in order to reduce the number of characters, mainly in Twitter or maybe in different SMSs, we perform some kind of contractions of our own. So this comes very naturally and to us, and we can typically remember those kind of things. So typically you will see words like tomorrow is contracted as TM. Then text me is also is represented as TM. Framed is can be represented as FRND, right? And so on. So these are some of the frequently used contractions that we as a sighted people also do perform. I mean, depending upon the situations, but you will notice that these kind of contractions are again not very random. I mean, we typically perform a certain kind of we follow a certain kind of rules to do these kind of contractions, and one of the rule is to remove the vowels, right? So given any word, like say tomorrow, if you remove the vowels occurring within this word, then the resultant word that you are going to get actually will have the same kind of pronunciation as the original word that we have. So if we can remove the vowels, so let's see. I mean, if tomorrow is one of the examples, so let's remove all the vowels from here, so it becomes T M R R W, right? So actually it is reflecting the same word. If you notice properly, then it can give us the original word as tomorrow. Secondly, I mean, there are conventions that if you have got a sequence of same characters, which is called as double letters, we can also remove them with a single letter. So tomorrow, again, since there are two R's, consecutive R's, then we can remove one of them and we can get like TMRW, which is very frequently used as a contracted form of tomorrow, right? So you can think about some other words and try to do this kind of contraction. You will find that these rules actually is helping you to get the contracted form. Similarly, if you consider this word friend, just remove all the vowels, so we are getting F, R, N, and D. So friend, which I have initially written, I mean, without looking into these kind of what are the vowels that are there in friend. Right? So these are some of the typical rules that we follow, and typically these rules are also incorporated for Braille contractions also. So in Braille also we normally use these kind of contractions by removing the vowels, repeated characters, and do the contracted form, so that it saves us a lot of space and gives us a cost-effective solution for that. So yeah, I mean, so this is a plain some more examples. So can you identify what are the original words for these characters? I mean, character sequences. Anyone? Can you try for some time? Okay. So I mean, if you have guessed CD as could, ABV as above, QK maybe quick, yes, and SD said. I mean, yeah, maybe it is difficult to guess what this particular sequence means, but this CD or ABV, PK, these are very easily recognizable as the original words as could, above, quick, and said. And you will see, I mean, in most of the cases, all the vowels have been removed to get this contracted form. Right? Okay. And these are the, I mean, examples of the dictionary that I was mentioning, that okay, I mean, so for every typically these English functional words, in English, like the determiner, conjunctions, prepositions. For them, I mean, we do these kind of contractions, and and there is a very strict, representation of all these frequent words with their shorted representation. Yes. So typically we have already observed now, I mean, how texts can be, textual contents can be, represented with terms of, with respect to Braille, and it becomes very easy for a person, for a blind person to, if they are knowledgeable about the Braille conventions, then it becomes very easy for them to, read and write textual contents that is written in a book. But typically, you will find in books or in any material, I mean, textual contents are not the only way source of providing information, but information can be represented in terms of images also. And to a large extent, these images are present in many of these sources, knowledge sources, right? Now the point is that, so textual representation with respect to Braille is possible, but the question is, can we have certain kind of representation for images? So how can a person is going to understand an image? To begin with, I mean, we don't have to think about very complex image of a scenery or a object or kind of thing, but to begin with, we can think about simplistic images in terms of geometrical figures. So when we are discussing, our main intention is in terms of their reading and writing capabilities for their educational purposes, and for that we can think about, initially we can think about representation of the geometrical figures like circle, triangle, square, rectangle, pentagon, etc. So can we have these kind of, I mean, some kind of way through which people can understand an image, or they can correlate an image with their conception. So one of the technique, I mean, so there are different kind of techniques. One is typically we call it as tactile graphics. Typically in many of these books you will find these tactile graphics are handmade by Braille transcribers, as using certain kind of plastic materials. I mean, these are some polymer which are used to create image representation of these objects. Right, but but the main problem is that these objects, object representations are normally handmade, and therefore, I mean, you can understand that it becomes a very costly process, time-consuming process, and you cannot generate something in bulk. So typically, when we are talking about building books with respect to Braille, so it becomes very challenging process to manually put all these image structures using these polymers in books, in Braille books. So one of the solution for that is similar to text, can we automatically convert images also in terms of Braille. And as a part of study, it has been observed that for simplistic, I mean, geometrical figures, it is indeed possible to convert images to actually to Braille. But again, I mean, these are for simplistic images, and you can see that these kind of images can be converted in terms of these braille dots. So these are typically nothing but typically the braille dots that you have already seen. So the issue is that how can we convert these things? So as I was mentioning, that if the images are simple geometrical shapes, then you can have certain kind of image processing algorithms and identify the image boundaries. Getting these image boundaries, after getting these image boundaries, you can identify the pixels and their positions, and you represent each pixel with a braille cell. Now, if you consider this particular line, I mean, there are millions and millions of uh, pixels can be there, depending upon the size and resolution of the image. But what we do is, we used to approximate these images and represent each of them. I mean, a bulk of image, a bulk of pixels with one single braille representation. So maybe in this particular figure, this portion of the entire image is represented by one single braille cell. Again, this portion is going to be represented by another braille cells, and these portions are going to be defined by you or your actually algorithm, and using which you can represent, right? You can have a representation of the image in terms of braille, and it becomes a very and once you can do it, I mean, efficiently, it becomes very easy for a person to to construct these kind of images, and they can put their fingers to understand, I mean, what the image is. Yeah, is there any question? Okay. So similarly, I mean, you can see, I mean, this is a triangle which again has been approximated, and they are represented in terms of braille dots. So some of the nonlinear objects, it becomes difficult for the algorithm. I mean, to correctly identify, to correctly approximate the positions of the pixels. And here you will see, I mean, particularly this particular region, which is a distorted one, these kind of regions cannot, I mean, the algorithm that we have used to construct these image, I mean, they fail to identify these non-linearity in the image, and here you will find, I mean, these things. This is a very linear representation, which actually it is failing to get these kind of distortions. Similarly, you will see that the entire image is not a very linear one. I mean, there is a difference in curvature at this particular position and this particular position. So those kind of things cannot be handled properly. I mean, maybe, I mean, the algorithm that we used during those days, I mean, they are not that much efficient in terms of identifying these kind of curvatures, and the approximation was really a simple one. So nowadays you will find, I mean, many complex and efficient approximators, which can give a better representation or braille representation for the individual objects. So this is another way or through which people can represent images, simple graphical images using braille. So apart from that, there is another technique, I mean, which which typically used to even construct complex images like Google Maps, or maybe a particular picture, a scenery, and so on, which a technique which is typically known as vacuum foaming, which takes polymer sheets, low cost polymer sheets, and using heat technology. I mean, so there is a technique involved in these, which is called thermoform, and they generate kind of heat to distort these polymer materials, and then they can have an impression of the entire images. So let me show you an example, but I don't know, I mean, whether how many of you will understand it. It would have been better if you can, have a physical class. So these are some kind of these polymer sheets where you can see, I mean, this is image representation of a map, right, where you will see, I mean, all the objects have been, embossed using these thermoform heating technologies over these polymer sheets, right? And these are the roads, these are the maybe the buildings which are there, and a person can have a fairly good idea about the map structure or the objects that we can have. Another way of incorporating such kind of things are um, you know building, utilizing the 3D printers. So say for example, we would like to have a concept of cubes, or a more complex objects like pyramids and so on. So those kind of objects can be 3D printed using a 3D printer, and the blind people can physically feel the objects to have knowledge of the environment, or the concept in general. So now the thing is that, so we can now we have some fairly good idea about how we can represent text to braille, and how we can utilize some of the algorithms to convert images to braille. Now the point is that we can have, utilizing these kind of technologies, we can I mean, utilizing these kind of techniques, we can create a technology which can be used to automate the entire process. So this is called the automatic transliteration of text to braille. And there is a very famous tool that is again, I mean, developed by IIT Kharagpur in the year 2002 probably, which is called Sparsha, which is a automatic transliteration systems from text to braille. So transliterating, I mean, English language text to braille is already there. So what Sparsha did is it developed technique to automatically convert English Indian language text to braille also. So we will discuss those things maybe in later time. But I mean, so overall, I mean, this transliteration process has got, I mean, this kind of architecture, which where you will see these are the input texts in Unicode encoding. So these texts are are passed to these transliteration engines. So these transliteration engines has got two different modules. One is got a forward transliteration, which converts an input text into braille, and there are mechanisms of reverse transliteration, which can have the input is in terms of braille, and it can be reverse translated to normal text, I mean scripted language text. So there are two different processes. One is the forward transliteration, and another is the reverse transliteration. So let's first see how this forward transliteration works. So this the mechanism of forward transliteration is pretty simple and straightforward. So what we have is, since we have already seen how individual text can be segmented into characters, and then characters can be mapped into individual braille cells. So that is the thing that we need to do. So given any editable English text, you have to identify the individual alphabets within the text, and corresponding to every alphabet there will be this is a forward transliteration rule engine which contains a list of dictionary kind of thing or typically we call it as a mapping file, which contains all these English alphabets like A, B, C, D, and corresponding to every English alphabet there will be a braille representation like this, and um, like sorry. Yeah, and this and so on. So these are the braille representations, and actually in these mapping file we don't represent these braille cells. We represent by their the position number as 1 1, then 1 comma 2, then actually 1 comma 2 comma 4, and so on. Yeah, so this is the actually the representation of these of the forward transliteration engine, the mapping file, which where you can see the input. I mean, there are two different panels, which is called the for each of these input alphabets there can be the Unicode encoding, or there can be the ASCII encoding of English alphabets. So these are the English alphabets like the A, B, C, D, and so on, and these are the braille representations which are actually in the form of these positional encodings like 1 1 2 1 2 4 and so on, right? And what we do is, so say for example we have got a text like mapping table, and we want to transliterate it into braille. So what we are going to do is we find the word the character M, which is a capital character. We will search in the mapping file where is the capital M, and then correspondingly we get its braille representation, and we replace this M by the braille cell, right? Similarly, we get a small lowercase a, we will search it here. What is the representation of the lowercase a? And then we are going to represent it here, and so on. So in this way, I mean, for all these braille representations, if it is a grade 1 braille transliteration, then for all these individual characters, we are going to have a braille representation text. So the entire process depends upon the construction of these mapping file. Now in English you will see these constructing these mapping files are very simple, because I mean almost in most of the cases for every individual braille cells there is, for every individual alphabet there is a very specific braille cells are there, but the process becomes very complex for if you are considering other language texts like say for example Indian languages like Hindi or Bengali or maybe Malayalam, Tamil. So where these Devanagari scripts are really very complex, and there are specific rules are there. I mean, so we have got vowels and consonants, and then in Indian language we have got a special thing like uh, consonant conjunctions. So what are these consonant conjunctions? So typically for vowels and consonants, representation of the braille cells are still simple, because in most of the cases for every individual character there is going to be a braille representation like this. And there can be for some characters there can be multiple braille representations. multiple braille representations, but but for these consonant conjunctions, typically the representation is little bit different. Say for example, I mean this particular consonant conjunction sha is actually written in terms of multiple characters. So we typically write ka, then halant, and then sha to form the construction sha. So when a system is going to read these particular conjunctions, I mean consonant conjunctions, it typically it didn't read this kind of things. What it read is these three representations, and for that either it has to do or these three kind of brain representations, or there are specific rules, I mean, which handles how to how to address these problems. So I'm going to stop it here right now, and in this class, and maybe in the next class we will discuss something more about how we deal with Indian language braille to text transliterations, and then there will be we will discuss about the process of reverse transliteration, and something more. So if there are any questions, I will be free to I will be answering. Otherwise, I will stop here right now. So any questions? Otherwise,
Okay,